Hello everyone. In the last session, we have finished unit number 7, that was Earth segment. In today's session, we will cover chapter number 8, that is satellite link design. In this chapter, first we are going to start a basic transmission theory. Now, first of all, what do you mean by satellite link design? So first of all, when we are going to establish a communication link, whether it is of having a wired or wireless, but if we are designing for communication link for a satellite communication, then we have to consider all the parameter, like what is my transmitting power and how this transmitter power will going to transmit it with a specific distance, what is its density, what are the different losses, what is a transmission medium. So before starting this, we are first focusing on the basic transmission theory, right? Now, we have to calculate what will be the power received by an earth station from a satellite, because it is the fundamental to understand the satellite communication. So first of all, we are considering a transmitting source in the free space. That means we have to receive a specific power. Then we need to consider that as some of transmitting source are present in the free space, which radiates a power that is PT in watts, which is uniformly in all the direction, right? So such a source is called the isotropic, because isotropic power means what? Okay, the power is radiated in uniformly in all the direction, right? So at the distance r meters from isotropic source, we are going to calculate a saturation flux density, right? It is represented as capital F. Okay, so capital F is represented like Pt upon 4 pi r square, as it is a flux density. It will be represented in the unit is watt per meter. This is the unit of saturation flux density, and this is the equation of saturation flux density. Okay, now our PT stands for transmitted power. That means a total power that we are going to transmit, and R stands for distance that we are going to cover. Okay, so the saturation flux density is represented by total power divided by the distance that covered by that power. Okay, over here it is represented as, with the help of diagram, our any isotropic source is presented which covers a distance r, and it is captured by a specific area of antenna, right? Area is A, unit is meter square. Okay, that's why the flux density is represented as watts per meter square. How much amount of power is there, and out of which area of the antenna that power is going to be collected, right? So this figure represents the flux density produced by an isotropic source, and the below figure, which represents the power received by an ideal antenna with an area A. So we can say that this is an isotropic source which radiates uniformly power in all the direction, and it is going to be received by the receiver. Okay, having a receiving antenna with a gain GR and area as a A. Okay. So if you want to consider that antenna's specific gain, okay, because whatever we are going to transmit, it depends on how much distance is going to be covered as well as what is the gain of my antenna. If we consider that for transmitter with the output PT watts, considering a lossless antenna with a gain GT, we are considering our antenna has a gain GT. So the flux density at a distance R is represented as simply multiplying the whole quantity PT upon 4 pi R square with GT. Okay. So this is the saturation flux density with considering the gain GT. And then it will remain the same, that is watt per meter square, as gain is unitless. Okay. That's why we can say that another term means the product of PT and GT is called EIRP, effective isotropic radiated power, which describes the combination of transmitting power and the antenna gain. Okay, its unit is watts because it is effective isotropic radiated power, right? If we are considering the receiving antenna with specific aperture, if it is having a meter square, then it decides how much amount of power is going to be collected by that receiving antenna. So the power collected, or you can say power received by that antenna, is simply multiplying saturation flux density with the aperture. Okay, over here. This whole quantity, this means saturation flux density is going to be multiplied with A. So F into A watts. So a practical antenna with the physical aperture area of A meter square will not deliver a power as given in the above equation. Why? Because we need to consider its physical aperture as well as its aperture efficiency. That's why we need to again derive this received power in terms of aperture efficiency. Its aperture efficiency is defined as sum of the energy incident on the aperture is reflected based on its effective aperture and its physical aperture. So the ratio of effective aperture and its physical aperture is called aperture efficiency, eta E. Okay, if AE is equal to A, then aperture efficiency becomes 100%. We can say that whatever the physical aperture is presented, all the area will receive the power. Effective aperture and physical aperture both are same. AE is equal to, so we can say that aperture efficiency of the antenna eta A is represented as AE upon capital A. If we are considering the parabolic reflector, then its aperture efficiency is 50 to 75 percentage. And for horn antennas, its aperture efficiency is 90 percentage, right? So from this, we can conclude that aperture efficiency of horn antenna is higher as compared to the parabolic reflector, or you can say dish antenna. That means its effective aperture is nearly having a value that is equal to its physical aperture. AE stands for effective aperture and capital A stands for physical aperture. Right? So these are the representation of aperture efficiency. Okay? Now, we are going to replace the value of physical aperture by effective aperture and aperture efficiency. So the power received by the real antenna with effective aperture area AE meter square is simply ER is equal to PTGT into AE upon 4 pi R square. Why? Because we need to consider what is its effective aperture. So we are simply multiplying over here. PT is already there upon 4 pi R square is already there. We are simply multiplying this F with AE. Why? Because we need to consider the received power. Okay. Then fundamental relation in the antenna theory is its gain and the area of antenna which are related by. We know that relationship between effective aperture and the gain G is equal to 4 pi AE upon lambda square. So we are simply substituting the value of AE by G lambda square upon 4 pi. Substituting the above equation in the equation A, this equation, right? We are replacing AE. So for AE is equal to G into lambda square on 4 pi. Right? And the value of A is going to be replaced over here. So GT, but that G is for receiving antenna. So GR into lambda square upon 4 pi. Right? So we can say that it's 4 pi R upon lambda's whole square. So PT GT GR upon 4 pi R upon lambda whole square watts. Right? Why it's watts? Because meters are going to be cancelled out. So this expression is known as the link equation. And essential is the calculation of power received in any radio link. So this is the received power. We can say that from this expression, received power depends on first, transmitting power, gain of transmitting antenna, gain of receiving antenna, how much amount of distance is there, between transmitting and the receiving antenna and its wavelength. Alright, so this is the expression for received power, and this unit is watts. So this expression is known as the link equation. If you want to consider how much amount of loss is there, path loss is there, so the term 4 pi r upon lambda square, this whole term is called path loss, right? So we are now collecting various factors. So we can say that power received is EIRP into receiving antenna gain divided by path loss, because receiving antenna gain is represented over there. Path loss, that is 4 pi r upon lambda. The whole quantity is represented by path loss divided by path loss. It is watt. So in this decibel, we can say that PR is equal to EIRP. As multiplication is there, if we are going to convert it into decibel, then we are going to replace it with the plus. And it is divided, that means we are going to replace it with the minus sign. It is minus of LP. LP stands for path loss. So EIRP is equal to PT into GT, but if it is represented in the dB, that means 10 log base 10 PT into GT dB watt. Okay, if it is GR, that means 10 log base 10 4 pi A upon lambda square. 4 pi A upon lambda square. And for LP, that is path loss, 4 pi R upon lambda, 4 pi R upon lambda whole square, and with 10 log base 10. So these three quantities are represented in the dB. All right. So over here, the basic transmission theory is finished, because it is an idealized case and there are no additional loss. Okay, but in practical, we have to consider all the loss, like atmospheric loss, free space loss, right? Attenuation due to the oxygen, water vapor, rain, everything. Okay, this is for the ideal case. So we can write it like the equation EIRP plus gain of receiving antenna, path loss, as well as attenuation in the atmosphere, loss with transmitting antenna and with the receiving antenna. So this is the power received in dB. Okay. So the received power is commonly referred to as the carrier power. So these links use the either frequency modulation for analog transmission and the phase modulation for digital system. So over here, basic transmission theory is finished. Still, if you have any question, you can ask me at any time on my this email ID. Thank you for your attention.